In 2014, an oil spillage from a pipeline managed by PEMEX led to a major spill that ended up contaminating the San Juan River. It was tragic at the time because it brought with it some side effects. First, the hydrocarbon spill. The quality of the water on the surface was severely affected, turning it into a toxic source for plants and animals that live there. Another big contamination was led to the soil around the lake. The oil seeped into the ground, and local farmers who relied on that land suddenly found their crops in danger. Sadly, from an accident, it quickly evolved to long-term damage to agriculture in the area. Now, let's talk about what and how many types of compounds exist in crude oil. Oil primarily consists of non-polar hydrocarbon compounds, which are made, as its name says, of carbon and hydrogen atoms with an even distribution of electrons, which results in very weak interactions with polar molecules like water, causing them to separate and not mix. This is called immiscibility, but this is something we will talk about later. A notable case is polycyclic aromatic hydrocarbons, PAHs, which have multiple carbon rings and can also be quite persistent in the environment. Alkanes, on the other hand, tend to be less toxic and are much more readily biodegraded naturally, and most can be ingested as food by some microorganisms. Asterisk, for example, the oil spill from the 2010 Deepwater Horizon BP well blowout was relatively high in alkanes and relatively low in PAHs. But, like all crude oils, it contained benzene, toluene, and xylene, which belong to the single-ring aromatic group. Benzene is very toxic and known to cause cancer, but is not as persistent as PAHs. Now we're talking about two fascinating types of molecules, benzene and polycyclic aromatic hydrocarbons, also known as PAHs. Let's dive right in. First up, benzene. It's one of the most important organic compounds and looks like a hexagonal ring with 6 carbon atoms. The cool thing about benzene is its alternating double and single bonds. But actually, these bonds aren't fixed. The electrons are delocalized, which means they spread out evenly around the ring. So, all the carbon-carbon bonds end up with the same length, a bond order of 1.5. That's why we often show it as a ring with a circle inside. Now, despite having polar bonds between carbon and hydrogen, the overall structure of benzene is nonpolar. This is because the ring symmetry cancels out any charge imbalance. Next, let's talk about polycyclic aromatic hydrocarbons, or PAHs. PAHs are just multiple benzene rings fused together. They share some similarities with benzene, like delocalized electrons and a planar structure. And just like benzene, PAHs are nonpolar. The symmetry and delocalized electron cloud help distribute the charge evenly, but why they don't mix with water? So, why don't these molecules mix with water? To answer that, as it was mentioned before, we have to think about polarity. Water is a polar molecule, meaning it has a positive side and a negative side. Because of this, water molecules love to interact with other polar substances. But benzene and PAHs are nonpolar. That means there's no charge imbalance in their structure, so water has nothing to grab into. The result, benzene and PAHs just don't mix with water, just like oil doesn't mix with water. But what about oil? That's where things get interesting. Oil is also nonpolar, just like benzene and PAHs. You've probably heard the phrase, like dissolves like, and that's exactly what happens here. Nonpolar substances, like oil and benzene, can mix together because their similar structures allow them to interact freely. So, while benzene doesn't mix with water, it can mix quite well with other nonpolar substances like oil. To sum it all up, benzene and PAHs are nonpolar molecules, which means they won't mix with water, a polar substance. But they can mix with oil, which is nonpolar like them. This principle, like dissolves like, explains why oil and water don't mix either. Let's dive a little deeper into the science behind the environmental problem and talk about the interactions between the substances. Understanding these interactions helps explain why oil spills are as damaging as they are talked about. First, let's start analyzing the oil, hydrocarbons. As we talked about, crude oil is a complex mixture of hydrocarbons made up primarily from carbon and hydrogen atoms. They range from simple molecules like methane to more molecules like benzene. The main thing you need to know about the intermolecular forces is that their dispersion forces are very weak, temporary attraction between molecules. Next, as said before, hydrocarbons are nonpolar, meaning they do not have significant partial charges, meaning they do not engage in stronger interactions like hydrogen bonding. On the other hand, we know that water is a polar molecule, meaning it has a partially positive charge on the hydrogen atoms, and a partially negative charge on the oxygen atom, meaning that the molecules mainly engage in hydrogen bonding. As you know, a very strong intermolecular force. When oil spills into water, it forms a thick slick on the water's surface, which blocks sunlight and reduces oxygen levels in the water, making it very difficult for the ecosystems that live under the lake to survive. Beyond this thick layer, some components of the oil dissolve in the water. Particularly benzene. Remember how I said it was very toxic? It is so toxic that it can kill the fish, damage ecosystems, and make the water unfit for human use. So guys, let's recap quickly, and reflect while we do so. To sum it up, a hydrocarbon is a chemical compound composed only of the elements of carbon and hydrogen. This compound works because the carbon atoms join together to form the framework of the compound, and the hydrogen atoms attach to them in many configurations. They are known to be the principal constituents of petroleum and natural gas, and serve pretty well as fuels and lubricants. Hydrocarbons have two categories. Alkanes that are saturated hydrocarbons with single CC bonds, and aromatic that have double bonds, just like benzene. Water is polar molecule with a bent molecular geometry. Right before we finish, let's just sum up the physical and chemical properties of both substances. Let's start with oil. Hydrocarbons can exist as a gas, like methane, a liquid, like octane, or as a solid, like paraffin wax. Their state depends directly on the size of the molecule. Smaller are gases, larger may be solids. Their boiling and melting point vary depending on the size of the hydrocarbon. As it increases, so does the melting and boiling point. Referring to its solubility, as we know hydrocarbons are completely polar, so they don't dissolve in water, they are less dense than water, that's why oil floats on water, and they tend to be more viscous, meaning they're thicker. Now talking about chemical properties, hydrocarbons are highly flammable and undergo combustion when they burn, meaning they release carbon dioxide and water. Now water. Water, as well as hydrocarbons, can exist in all three states, but it's especially liquid at room temperature. Water has a high boiling point of 100 Celsius and a melting point of 0. Of course, water is often called the universal solvent, because it can dissolve so many substances. Its polarity allows it to break apart and interact with more polar molecules. But just polar though. These differences may just explain why oil floats on water, and why it is so hard to clean up. These differences explain why, during oil spills, oil floats on water and is so hard to clean up. It's these properties that drive the environmental challenges we face when dealing with oil spills. Now let's talk about a method to clean water. Today, we'll look into nanofiltration, or NF for short. Let us break it down into a few simple steps. Nanofiltration is a membrane filtration method with holes ranging from 1 to 10 nanometers. Consider it a filter that stands somewhere between reverse osmosis and ultrafiltration in terms of pore size and removal capacity. Here is how it stacks up. Reverse osmosis, RO, has the smallest pores, about 0.1 nanometers, allowing it to remove practically everything, including minuscule ions. It's ideal for desalination and high purity applications. Ultrafiltration, UF, contains bigger pores, ranging from 1 to 100 nanometers. It is used to filter out bigger particles like bacteria and viruses, but not dissolved ions or small compounds. Nanofiltration, NF, falls somewhere in between, successfully removing organic molecules and multivalent ions but not all monovalent ions. So, why consider NF? Here are a few advantages. Selective removal targets specific ions and chemicals, making it perfect for precise water treatment. Reduced chemical need. If you remove impurities more efficiently, you may need less chemicals. Electricity efficiency. NF requires less pressure than Rho, which saves electricity. Improved water quality. It aids in the removal of organic compounds and hardness-causing ions, resulting in superior water quality. However, there are several drawbacks. Membrane fouling. NF membranes can become foul with organic debris or scale, necessitating additional maintenance. Limited ion removal. Compared to Rho, it removes fewer monovalent ions. Initial cost. Setting up NF systems might be costly, but you may save money on operating expenditures. Waste treatment. NF generates concentration streams that require adequate treatment. In conclusion, nanofiltration is excellent for targeted contaminant removal with minimal energy and chemical use. It's an excellent choice for certain situations where precision is essential,